If you're hearing me, just thumbs up. Let me know you're hearing me. If you're hearing me, I want you to thumbs up so that I will know you are hearing me. And I will look at what as a mode of check. Fantastic. I can see Caesar. I keep seeing Caesar. I keep seeing Caesar. I keep seeing Caesar. Who else is hearing me? Who else is hearing me? Is Mr. Isaac hearing me? If Mr. Isaac hearing, let him thumbs up. Let me know you are hearing me. I only have 4 people here now. I only have 4 people here. Mr. Caesar, have you been able to picture 1 or 2 things for what I've been saying? If you do, thumbs up, let me see. If you do, thumbs up, let me see. I can see Hamza. I can see Hamza. So we will still have to do this class again. But before we do this class again, let me have a summary of what I've been saying. Let me have a summary of what I've been saying. What I've been saying since the beginning of this class, is an analysis of variance. An analysis of variance. How do we perform analysis of variance in our experimental design? How do we perform analysis of variance in our experimental design? We have many types of analysis of variance, but we'll be speaking to one-way analysis of variance, which is CRD. Two-way analysis of variance, which is RCBD, and three-way analysis of variance, which is Latin square. CRD is called completely randomized design. CRD is called completely randomized design because it involves it is called one-way analysis of variance. Am I speaking sense? If I'm speaking sense, thumbs up, let me know if I'm speaking sense. I can see fantastic. I can see Mr. Caesar. I can see Mr. Isaac. It is called one-way analysis of variance because the experiment is interrogating only one source of variation. The experiment is only interrogating only one source of variance. The experiment is interrogating only one source of variance. And that is why it is called one-way analysis of variance. That's why it is called one-way analysis of variance, because only one source of variance is involved. If it involves two sources of variation, then we call it RCBD, randomized complete block design. Why do we call it RCBD? Why is blocking? Because when you've got more than one source of variation, you begin to block. Begin to block into possible source of variation. That is when you'll be able to pinpoint variation in your population to a particular independent variable. Like I said, independent variable provoke responses independent variable. So, example of one source of variation experiment is effect of diet on egg performance of chicken. In that sense, you make sure that there's obviously a layer chicken is a male, is a female. Then you have eliminated no issue of sex. So that when in totality of the experimental design, there's only one sort of variation. That's why I call it one-way analysis of variance. Am I speaking sense? Am I speaking sense? Am I speaking sense? Am I speaking sense? Fantastic. Fantastic. That's why it is called one-way analysis of variance. Now, when you're expanding your experimental design, it is involved in more than one sort of variation. Then blocking will come into it. What is blocking? Blocking blocking tells us about let me say the principles of orthogonality speaks about blocking. The principle of orthogonality speaks about blocking. The principles of orthogonality speaks about blocking. What are the principles of orthogonality says? Principles of orthogonality says it provides for elimination of heterogeneity. Blocking is elimination of heterogeneity. Blocking is done when you have possible, you have more than one sort of variation that can affect the outcome of your experiment. Then you block. Block means eliminating heterogeneity. Other factors that can affect, that can cause variation in your population. So that you not be misled. For instance, you put together animals of different breeds, animals of different age, and you are testing diet. What you're going to find out as effect of diet will not be correct, will not be true, because effect of age may affect good performance. Effect of sex may affect good performance. That's where blocking comes in, and that's what principles of orthogonality provides for: elimination of heterogeneity, contaminant, possible source of variation by blocking them into experimental unit, so that you make your experiment more homogeneous. When you block, you try to make your experiment more homogeneous. When the more homogeneous your experimental design is, then the more you can rely on the independent variable you are interrogating. You make sure that every other source of variation that may affect the outcome of the experiment, you have blocked them. That's what principle of orthogonality says. It provides for elimination of heterogeneity, which is meaning contaminant, by blocking them into homogeneous units, by excluding all forms of contamination that may interfere with validity of your experiment, and this increases precision of your conclusion. Am I speaking sense? Am I speaking sense? Am I speaking sense? So that leads us to RCBD, randomized complete block design. So that blocking is separating them, is eliminating all forms of heterogeneity that can affect your outcome, or possible sort of variation. And that's how we call it randomized complete block design. For instance, effect of age, effect of sex. You have effect of sex, effect of age, effect of breed together. So you block them. So all animals of the same age, you block them. All animals of the same sex, you block them. All animals of the same breed, you block them. Then you not provide for effect of age in the experiment, effect of sex in the experiment, and effect of breed. And there will be interaction between these possible sources of variation, because all of them will interact together to affect the outcome of the experiment or the dependent variable you are measuring. Am I speaking sense? Am I speaking sense? So this makes your experiment more reliable. It makes your experiment more reliable. So anybody who does similar things will find the same result. So the findings of your experiment will not be misleading. The findings will not be misleading, because all contaminant, which is regarded as source of variation, has been blocked. So you can be doubly sure to interrogate individual effect of the independent variable. Then we move to Latin square. So one way, that's why we regard RCBD as one-way elimination of heterogeneity, meaning that beside your main effect, of the independent variable, you can block other sources of variation. You can't have to block other sources of variation. That's what blocking. And you interrogate those ones too. Then we move further to Latin square, which provides for more than two sorts of variation. And that we call Latin square two-way classification of heterogeneity. We call Latin square two-way classification of heterogeneity. We call Latin square two-way classification of heterogeneity because it involves blocking of the experimental design into more than one categories of factors that can influence source of variance, that can influence the outcome of the experiment. And this is the intricacies of analysis of variance. So when you get this very well, it will be easy. It will be easy for you to be able to identify what is causing variation in your population. And we have assumptions. We have assumptions of Latin square, assumptions of RCBD, assumptions of CRD. And what are the assumptions of CRD? Number one, error terms are randomly and independently and normally distributed around the mean. In every experiment, there is error term. There is residual error. Because an experiment cannot be so perfect that there won't be error. Though you must do all you need to do to eliminate every possible source of error. But some error can come in. For instance, you are doing effect of temperature, XC2, and suddenly rain began to fall during the period of experiment. You have nothing to do about it. Rain will fall and sun will shine again. Or during you have nothing to do about it. You can't control. It's a natural occurrence. Remember, you're doing an XC2 experiment. Maybe during the process of the experiment, one of the animals or two of the animals fell sick. You can't do anything about it. They will feel when they fall sick, they may not be able to perform the way they're supposed to be, even when they're not sick. They will get well again. When they were sick, the data they will produce will be affected. Or some dies. When some die. So causes with error that may come outside the control of man falls under residual error. So that's why we say error term is randomly, independently, and normally distributed around the mean, because the reliability of the mean is determined by the error. The higher the error, the less reliable the mean is. The lower the error, the more reliable, the more true the mean is. We can rely on the mean and make justification and make recommendation and make inference with the mean. Am I speaking sense? Am I speaking sense? Am I speaking sense? So the error, that's why when you see your result, you must add error terms. Maybe 40.12 plus or minus 0.002. That error is to tell us how reliable that mean is. So the lower the error, the more reliable the mean is. We can rely on the mean and make inferential judgment, reliable judgment. Number two is variance of different samples are homogeneous. We want to believe that the variances, variances is to measure variation. So differences between them are the same. They are the same until your independent variable comes in to provoke responses in your dependent variables. For instance, effect of you are changing temperature, effect of thermal assault condition, which is temperature, on thermotolerance traits of Nigerian cattle. And if you want to measure thermotolerance, then you measure rectal temperature, you'll measure body temperature, you'll measure respiratory rate. These are the thermotolerance parameters for you to measure thermotolerance of your animals. When you increase temperature, how do those animals respond? You can know their response to increase in temperature by those thermotolerance traits. So we assume that the variance between them is the same until source of variation is provided. Until independent variable is provided. Am I speaking sense? Am I speaking sense? Am I speaking sense? Fantastic. So variances of different samples are homogeneous. Normality. Samples are taken from normally distributed population. No bias. Your population must be free of bias. The condition of population must be normally distributed. Number 4 is variance and the means of different samples are independent. Variance and means of different samples of different population are independent. And number 5, independent variables are independent of each other. But this one, okay, let me say all this one I've been saying, they are both assumptions. They are both assumptions of RCBD and CRD. All that I've been saying, they are both assumptions of RCBD and CRD. But when it comes to independent variables are independent of each other, that speaks to RCBD alone. That's one of the assumptions of RCBD alone. Independent, because in RCBD we have more than one source of variation, and this source of variation act independently of each other. The responses they are provoking in your experiment, they act independent of each other. They don't take permission from each other. Effect of breed will manifest itself differently. Sex will manifest itself differently. So independent variables are independent of each other. But this is particular for RCBD. This is particular for RCBD. Am I speaking, sir? Another one is treatment effect are additive for RCBD alone. When I say treatment effect are additive, meaning that we have more than one source of variation. That's one of the assumptions of RCBD. Am I speaking, sirs? Am I speaking, sirs? Am I speaking, sirs? Am I speaking, sir? Another assumption of is this. I've talked the independent variables are independent of each other. Treatment effects are additive. Those are the two unique assumptions for RCBD, while others are assumption of the two. Let me further give you another one. I told you initially. Let me just run through again. I said treatment effect is fixed. Another one is treatment effect is fixed. Because the effect of treatment is fixed. Treatment effect is fixed. Treatment effect is zero. We don't expect that. We don't expect what the treatment will give us until we'll use it to provoke response in the animal. So treatment effect is fixed. Treatment effect is zero. Error times are randomly distributed around the mean. Variances of different samples are homogeneous. Samples are taken from normally distributed population. Variances and means of different samples are independent. These ones are both assumptions of RCBD and CRD. The only difference is independent variable act independently of each other. That is for RCBD alone. And treatment effect is additive. That is for RCBD alone. And look at the assumptions of Latin square. Let me give you assumptions of Latin square. These assumptions are the ones that tell you which when you are confronted with the experiment design, the assumption will let you know which type of design you will adopt. Take a look at Latin square. Latin square has more classification of heterogeneity than RCBD. Look at assumptions of Latin square. Treatment is set in rows. I'm going to explain further. Treatment is set in rows and columns. That is a constant variance. Treatment, rows and columns are additive, and there's no interaction between the factors. And there is normal distribution. You take your sample from a normally distributed population, meaning that you don't provide for bias. You don't provide for bias. So these are the background information you have to know relating to analysis of variance. Am I speaking sense? Am I speaking sense? Am I speaking sense? Am I speaking? So when you get all this correctly, it will be easy for you to analyze variation in your experiment. So what you must make sure you, if you experiment, especially in breeding experiment, if breeding experiment always involve more than one source of variation. No, you can figure effect of sex, effect of breed, effect of location, effect of diet. So you block them. The more you block your experiment, the more you make it homogeneous, and the more it make it homogeneous, the more reliable the independent variable, the means you are measuring, the more reliable they will be. So I'm going to stop here today. Next class, I'm going to come with the data that we'll use to calculate all of this. They calculate. Calculate your perform analysis of variance. You know the F value. You know the level of significance. You know the F value. You know the mean value, and you know the F value, and you know the F calculated, and you know the F tabulated. So in the next class, I want you to come with F table that we will use to do some real life, do some calculation on some real life data, so that I can brighten your understanding about analysis of variance. Am I speaking sense? Am I speaking sense? Am I speaking sense? Am I speaking sense? So I will generate the summary of this class and give to Mr. Isaac and share with you. So please, I want you to familiarize yourself with this online class, so that we will have an interactive discussion. And I can assure you, with what I've put together, at the end of this class, your understanding of simple or basics of experimental design, especially involving analysis of variance, will be fantastic. So thank you for your time. Tomorrow, let me see. Let us make it 1 o'clock tomorrow. 1 o'clock tomorrow. 1 o'clock tomorrow. Then we'll reconvene again. Thank you for your time, and God bless you.